All right, welcome to our last review, end of year final review part 4. This review is going to go over just the different types of functions that we've seen this year. Key features, so when you draw the graph, can you identify the different intervals, domain, range, and so on, and then solving quadratics. So I'm going to break this into 2 videos. The first one being kind of this front page, and then the second one being more on the solving quadratics. Okay, so let's start 1 through 6 here. For each equation, first state whether the following equation is linear, exponential, absolute value, quadratic, or a circle. Then explain why. So what about the equation makes it so? So first of all, you could graph these, right? You could identify that one makes a parabola, one makes a circle, one makes exponential. And if that's helping you, you can go ahead and do that. But looking at the equation, we want to identify why we could tell from that. So let's just look at this first one. Notice that on this first one, you've got an x piece here that's being squared, and you've got the y piece here that's being squared, and then it's equal to this value. This one that we're looking at, right, when we have an x squared and a y squared, is a circle. So we want to make sure that we're familiar with looking at this and saying, okay, if we have x squared and y squared, that's not a parabola, that one's a circle. So maybe my reason would be both the x and y are squared. Okay. Looking at number 2, notice this one looks different than ones we've dealt with a lot this year. You guys did these last year a lot. But y isn't squared, but x is up here inside the exponent. So when the variable jumps up into the exponent, right, these ones we called exponential. So this would be an exponential equation. And why is that? Well, if we ever see the variable, right, is in the exponent, then we know that it's going to be an exponential function there. Okay, those two are pretty distinct. We can identify them pretty straightforward. Number 3, if you look at this one should look familiar. This one has an exponent of 2, and it's only on the x piece, right? So y isn't squared, just x is squared. So that means that this is a parabola, right? This one has a degree of 2, or the x is the squared piece. So this one is a parabola, and we call parabolas the quadratic functions. And that one we call vertex form, right? So we're looking at this one. This one has the degree of 2, is 2, or again, you could say x is the only squared piece, something along those lines that help you to identify what you're looking at there. Again, on 4, so if we're looking at 4, notice that this one, right, neither of the variables are squared. X just has like a variable of 1. So anytime we graph something where x is a variable of 1, this is like the form y equals mx plus b, right, where there's just one x there. This creates a linear equation. So again, we've done some of those this year. You saw them a lot last year. These will create straight lines. So a linear equation, the degree of the function is 1. Okay, always, always. Number 5, again, if we look at this has multiple x pieces, but if we look at the degree of the function, again, the degree is 2. The highest exponent is 2. So whenever the degree is 2, again, we're going to have a quadratic function. So both 3 and 5 are quadratic. They're just in different forms. Again, this reason being, right, that the degree is 2. The degree always tells me what kind of function it's going to be. Lastly, number 6, this one, again, is pretty easily identified. These we call absolute value bars. So in this case, when we graph this one, this will definitely be an absolute value function. And when the x is inside the absolute value bars, then it creates an absolute value function, or a V-shaped graph. So, right, the x variable is inside absolute value bars. Whoa, that's an O. Man, my throat. All right. Those are the different types of functions, so make sure that you're comfortable with identifying each of those. 7 and 8. So we're going to look at graphing. Again, the quadratics on this side, we notice that's a degree of 2 again. Number 8 would be an absolute value function. So you're going to draw the graph, and then we're going to identify these key features. So practicing using that notation once again. So let's start with maybe number 7. And we want to identify, first of all, the vertex so that we can go ahead and graph this function. Remember that to identify the vertex, the x value piece is always going to be negative b over 2a if it's in standard form. Now, when we do that, right, x is equal to negative b. Well, what is b? B is this value right here, right, the negative 8. So if it's negative 8, we're doing opposite of b. So we're going to do positive 8 over 2 times a, and a is this little piece right here. So a is negative 2. So we've got 8 over 2 times negative 2, which is negative 4. 8 divided by negative 4 is a negative 2. So my x value of my vertex for this parabola is going to be negative 2. Then how do we find the y? Well, we plug it back in, right? We say, well, what is y equal to if we were to put the negative 2 in for x? So we've got negative 2, and we put it in right there every time we see an x value. Then we've got minus 8 times x, and again, we're going to put in the negative 2 for x, minus 4. And then if we simplify that, we've got negative 2 squared is 4 times negative 2. We've got negative 8 here. A negative 8 times negative 2 is a positive 16, and then negative 4 on the end. And then if we combine all of that together, we end up with a positive 4. Now again, you can graph this using your calculator or Desmos. You guys remember Desmos? I feel like I used this one quite a bit in class, but if you want to use Desmos, you can graph them as well using that. All right, let's go ahead and plot this. So if we plot our vertex, right, is at negative 2, positive 4. So it's going to be right here. And then this has been stretched by 2. We know it's upside down because of that negative, right? It's opening down, and it's stretched by 2. So normally if you go 1 unit away, it's up 1, but we're going to double that and go up 2. Okay. Normally when you're 2 units away, 2 squared is 4, so it would be at 4 units up. But we're going to go 8 because this one's stretched or doubled. Okay, so our parabola here, okay, I'm going to try and draw that. Will look something like that. Okay. All right, let's identify these pieces. So part B is asking us to find the vertex. We already found the vertex, so we're good there. Negative 2, 4. Again, remember the vertex is that high or low point there. That one would be a maximum at the top. Part C is asking us to find the y-intercept. So if you look at the graph, where does it cross the y-axis? Right there, where it's touching. So we're going to have the point 0, negative 4. That would be our y-intercept. D is asking for the domain. So remember the domain of a parabola. We loved this because domain was all real numbers, right? Any x value works inside of this. It gives us a y value output. So this one was negative infinity to infinity, or we can say all real numbers. Those mean the same thing there. Okay, looking at E, we're asked to find the range. So remember, range are all of the y values for which the function is defined. So range are y values. So if we notice our graph is pointing down, right? It's kind of like coming from down here at negative infinity, and it goes up and up and up and up. Our graph is always underneath this like invisible ceiling. So we could say from negative infinity up to 4, because we always go least to greatest. So we can write it in that way, negative infinity up to 4 with a bracket. Or some of you like the inequality notation better because it kind of makes sense. Y is always less than or equal to the 4. It's always underneath that y is equal to 4 value. Okay. F is asking for the increasing interval. So where is our function increasing? And then I'm going to kind of do these at the same time. So g was decreasing. Remember, increasing and decreasing, we move left to right. And we're talking about if we were to draw, right, the little guy that's going for a hike. Is he going uphill or downhill first? Well, in this case, he's going uphill, right? He's trying to reach the peak here. And so from negative infinity, he's walking uphill until we reach -2. So at this place right here, right, he's going to start to go downhill. So we're going to say he's increasing from negative infinity until 2. Or if you want to use the inequality notation, you could say always on the left side of -2. And again, if you think about that less than, it's pointing to the left, right, the left side. Decreasing then is the other side of the function. So once he reaches the peak, he starts to walk and he's going downhill on this side. So from -2, he goes downhill forever, right? And these are positive values over here. So we're going to say from -2, oops, I should have put a negative on that one, sorry, to positive infinity. Or again, if you want to use inequality, we're saying always, okay, that's backwards, where x is greater than or pointing this way from -2. Again, I didn't ask you for the axis of symmetry, but just recognize the axis of symmetry, right, is where those increasing and decreasing changes. So axis of symmetry would be x equals -2 on this one, where it cuts it in half. Last thing it asks you for is transformations. So transformations, we said, how is this different than the parent function? So remember, the parent function of a quadratic and all functions sits here at the origin, and we're looking at it coming up this way, right, and this way. So how is the graph we drew different from this one? Well, first of all, it's upside down, so we call that a reflection. Secondly, the vertex moved this direction too, and then it moved up, right, 4 units, so that it was sitting right here. So those are all transformations, and then notice this one's steeper, so it's stretched by 2. So those are all things that I'm going to list down here. So again, the first one may be the reflection. Reflected over, so now it's pointing down, right? It also shifted left 2 and up 4. Okay, that took the vertex over to -2, 4. And then lastly, there was a vertical stretch by 2. Okay, those 4 transformations would identify and tell us what happened to that parabola. All right, key features. I know notation. Hopefully this gives you a great example of what you're looking for there. Again, if my parabola was opening this direction, right, the vertex is now down here. My range now is going to go from here up to forever. My function is now decreasing on the left side and then increasing. So some of these things will switch and change, but essentially you just have to identify the specific parts for the function you're looking at, okay? Number 8, I'm just going to start by graphing that one, and then you can identify the features to finish it off. So number 8 is an absolute value function. Again, I know that it's going to be a v. This one is in vertex form, right? So we've got our h here and our k, and remember the vertex is always like the opposite of what we see there as h and then k. So if I want to graph this one, I know that the vertex of my function where I'm going to start graphing is going to be at the opposite of the -3. So it's going to be at 3, and then my k value at 3. So I'm going to go +3 up 3. That's going to be the vertex of my absolute value function. Then I'm going to use the slope out front. So this works like a linear equation. My slope is -3. In other words, it's opening down to create the V shape. So I'm going to go down 3 over 1, right? It has a slope of 3. 1, 2, 3 over 1. And then we do the same thing in the other direction to make this a symmetric V. Okay, so absolute value functions are even easier to graph than quadratics because they've got linear pieces. So there's our function. So again, you're going to go ahead and identify the different parts. It looks like we did part A, graphing, and then we did B, and you're just going to continue on with the rest of this one. Okay, great job with that. Work through those. If you have questions on any of those pieces, I know it's been a little while since we covered them, let me know.